Okay, I'll come look at it in just a second. Okay guys, this is the application problem that I instructed you to review. Go ahead and pause the video if you need to so that you can read about the situation that's going on. Okay, so now that you've had a chance to internalize what's being asked, I'm going to draw a picture over here. Here's your piece of cardboard, and the cardboard measures 18 by 18 on every side. And in part A, we're told that we are taking that cardboard and removing a 1-inch square from every corner. So these little pieces, I'm grabbing some scissors, cutting out. And those measure 1 inch on every side. Then in part A, you're just asked to find the volume of the box that's formed if I cut and fold up. So I'm kind of folding along these horizontal dashed lines and vertical dashed lines all the way around to form an open top box. If you'll recall from geometry, the formula for volume of a box is length times width times height. In this case, it would look like the length is 18, but remember I'm snipping here 1 inch off each side. So the length's actually 16. Same thing for my width. It looks like it would be 18, but I'm snipping 16 to get a total of 16. And then the height, if I fold that up, I'm going to try to draw that. Give me a second. I'm going to pause my video and try and draw. Alright, so here's my horrible attempt at a picture. And what I'm seeing is that when I fold these sides up, I'm getting the length and the width of 16. And the depth right here of the box, according to my picture before, that's where I'm folding up these sides. So that depth is actually 1, the 1 inch. So I've got 16 by 16 by 1, or 256 cubic inches for the answer on part A. Now that's just a nice scaffold to help us out where we arrive at this next problem. We want to represent that volume as a function, this time assuming that we cut off a piece from each side that's not 1 inch long, but X inches long. So that means when I'm looking at this picture up here, things change. And these values are no longer 1, instead they're X. So that makes life a little bit more complicated, but more interesting in my mind. So I'm going to grab my eraser then, because then I don't know that these are 16. And in fact, what I see here is that this base, which measured 18 before I cut anything, is now going to just be 18 with those x's removed. So I'm going to have to account for that with 18 minus 2x, 1x from each side.
What are you doing?
That's my daughter Eliana. Say hi. Hi. I'm going to explain something to my students real quick, okay? The width is additionally going to be represented as 18 minus 2x because all we know, hold on baby, I'll get you one, is that we're removing an x from each side. The big kicker here is that this value right here is not 1 inch anymore. Now we just note that with an x. So the volume, which is still length times width times height, is 18 minus 2x, 18 minus 2x, and another x. So that ability to write a function about an open top box is one that's directly aligned to a problem you're going to see tomorrow. And assuming I give you the dimensions of the original piece of cardboard, this is always going to be true. You're going to take that dimension, remove 2 x's from the length and the width, and the height is going to be that x. Then the next logical question for me to ask is what value of x maximizes the volume, and what is that maximum volume? So what I'm going to do here is open up a calculator, and I'm going to graph the function that we just came up with. It's going to be 18 minus 2x, another 18 minus 2x. Okay, Eliana, can you hold on a second? And the x. When I graph, we talked about this earlier, but we know that that is not an appropriate viewing window for what I should be seeing. Here, take it and walk away. Thank you. I'll be with you in just a minute. And if you'll notice, my calculator starts with a viewing window of -10 to 10, which I told you guys was like a default to start with. I'm going to go ahead and change the y's to -10 to 10 as well. So again, you can see that like the y value is clearly not high enough because I'm not capturing the maximum that exists. So I'm going to go down to y max. and maybe make that like 50 and see if that is appropriate. And you'll notice I'm starting to see more, but not enough. So I'm going to keep going. And maybe I'll try 100 this time to see if that maximum captures the high point. Oh goodness, this maximum is huge. So I'm going to continue going. Maybe I'll try 200. Getting better, but not close enough. So I'm going to just continue adjusting that Y maximum. Notice I am not hitting zoom at all. I'm just manually adjusting the max. Oh, I'm so close. That was 400. I'm going to try 500 this time. All right, there's my max. And this last question was just asking us to figure out what dimension the maximum occurs at and what that maximum is. Just a second. All right, so here's the high point. Sorry, I had to take a break there. And when we ask for the maximum volume, the nice thing is this is always going to be menu number 6, maximum. I could ask you for a minimum. This time I ask you for a maximum. And I select that option. Calculator wants to know lower bounds. Some of you have been confused about this. You just need to go somewhere to the left of that maximum, but not way out here. That's going to go way too far for your calculator to understand that you want to find the maximum over here on our graph. So just a little bit to the left, a little bit to the right, and our calculator's maximum will appear. It's at 3,432, which means to answer this question, what value of x maximizes the volume? That's the value x equals 3 inches. And that maximum volume is 432 cubic inches. And that's that. But if I had to address or highlight anything, it would be your ability to write this function right here and translate that to a graph to find the maximum value. Awesome. This next question is from page 53, and it's our average rate of change example. So we're talking about the distance in feet that an object travels when dropped from a high place, and it's given by this formula right here. D of t is negative 16t squared. T is in seconds, and we want to find and interpret the average speed, or average rate of change, that's just another way of saying average rate of change, of the object from 2 to 4 seconds. When I read this, I'm taking away that the interval that I've been given is 2 to 4. So the first thing I'm doing is identifying that that's my A and my B. I'm recalling that average rate of change is simply f of B minus f of A over B minus A. More specifically to this question, that is going to mean we have D of 4 minus D of 2 over 4 minus 2. I'm going to open up a calculator page and I'm going to graph my function. I was just working on another problem, so I'm actually going to go back to my default window of negative 10 to 10 everywhere, although I'm not super concerned with that. I'm going to hit tab to get my function bar in, and I'm going to type negative 16x squared. Be careful that you don't type a t. Calculators don't understand t's. And there's my graph, which is awesome, but I don't really care what the graph looks like. Remember, for an average rate of change question, the goal is to link that graph to a calculator page and then to hit Control Divide and set up your template for the average rate of change. That's variable f1 of 4, scroll over, minus variable f1 of 2, go down, over 4 minus 2. My calculator does all the work for me, and I get an answer of negative 96. That's one point, and your second point comes from your sentence, which is much harder to earn. I'm going to model this one more time. From 2 to 4 seconds, the distance, you have to tell me what it is that the problem is about, is... That's okay, baby. I'm almost done with this one. The distance is, since I got a negative value, I'm going to use the word decreasing. Had my answer been positive, I would use the word increasing. The next phrase is non-negotiable. At an average rate of. I have to see that phrase when you explain an average rate of change question. Next is the number, 96. I'm not going to put the negative because I use the word decreasing. And finally, my units. Remember, I'm talking about a rate, so my units have to indicate that I'm dealing with a rate. And the distance here was measured in feet. the time was measured in seconds. That's it. Full credit if you can get me that sentence.